All right. Hi, everybody. Welcome back. Thank you for joining us today for our high energy phenomena seminar. Hopefully we can give you all a break between refreshing the news. We won't talk any more about that now. So today we have two wonderful speakers. Without further ado, let's get started. Our first speaker is Dr. Congyao Zhang. He received his PhD in 2016 at the Kavli Institute of Astronomy and Astrophysics in Beijing. He was then a postdoc at MPA Garching with Dr. Eugene Shursov. Since 2019, in 2019, he started his second postdoc at the University of Chicago, working with Professor Arina Zurovleva. His research interests include galaxy clusters, large-scale structures, and cosmology. So please take it away.
Thank you. Share my screen. Can you see my screen? Great. Hello, everyone. I'm Congyao Zhang. Today, I'm going to talk about runaway merger shocks in galaxy clusters. And my main collaborators in this project are listed here. So I will start my talk from mergers of galaxy clusters. They are extremely energetic events in the universe and play an essential role in the cluster growth. You may have seen this beautiful image many times. It shows one of the most important examples of merging clusters, the bullet cluster. The red and blue colors show you the distributions of the hot gas and dark matter in this merging system. One basic but important fact about cluster mergers I want to emphasize here is that they are always supersonic. The argument is simple. It's just because the free fall velocity of galaxy cluster is always comparable or larger than the sound speed of the intercluster medium. So during the merger process, merger shocks are naturally formed, but the typical Mach number of the merger shock couldn't be too large, usually smaller than 3 or 4. So here again, I use a bullet cluster as an example. In this X-ray image, you can clearly see the X-ray, the merger shock in this image here. In the right panel, I show you the gas profiles measured along this horizontal direction. So you can see the shock front is here, and there is another edge, which is a contact discontinuity. It's also known as the cold front in merging clusters here, which separates the gas halos of two merging clusters. And moreover, both the cold front and shock front together constitute are the solutions of hydrodynamic equations at the surface of discontinuity, which includes 3 equations: the conservations of mass flux, momentum flux, and energy flux. So actually, the contact discontinuity corresponds to a trivial solution of these 3 equations, where the gas velocity is 0 as a rest frame of surface. But the shock corresponds to a non-trivial solution. Both the gas velocity and pressure are discontinuous at the surface. And in this slide, I'll show you a simulation of a merger between 2 idealized galaxy clusters to illustrate how the merger shock and cold front are formed during the merger process. And in this simulation, there are 2 idealized clusters. Each one is assumed to be spherical and is composed of gas halo and dark matter halo. So you can see in this movie, the left panel shows the X-ray modeled X-ray image, and the right panel shows the modeled X-ray weighted temperature distribution. You can see a subcluster enters into the main cluster from the top left, and the gas field of the main cluster is significantly disturbed by this infalling subcluster, and the entire system spent a few gigayears to recover its visualization. And 4 snapshots from the previous movie are highlighted here. The black dashed lines show you the trajectory of the infalling subcluster. The black arrows mark the positions of merger shocks. And the boundary separating the gas halo of the subcluster and the atmosphere of the main cluster is a cold front here. So you can see in the first 2 panels, the cold front and shock front move together along the same direction. But after the core passage, the subclusters start to decelerate, and it eventually falls backwards after crossing the epicenter. But in the meanwhile, the merger shock all the way moved to larger cluster radii. So you can see in the third and fourth panels, the distance between the cold front and the shock front becomes larger and larger. So in this process, the merger shock experiences a transition from a bow shock to a runaway shock. So we can also summarize the formation and evolution of merger shocks as a two-phase process, the driven phase and detached phase. An important point I want to emphasize here is that in the detached phase, the subcluster has only limited impact on the runaway shock, whose propagation is mainly determined by the surrounding atmosphere. So an important feature of the runaway shock is that it could be long-lived while moving down a steep gas density gradient. So we can actually simply understand this feature in the following way. Without loss of generality, we can assume the gas density profile of the atmosphere follows power law. Omega is the index. So if we see a propagation of a linear wave, its energy is always conserved, which could be written as rho r square u square. R is the radial position of this wave, and u is the gas velocity of the wave. So you can see if we check the gas velocity derivative with respect to the radial position, the eta is always a function of omega. We show it as the green line in this eta omega diagram. So you can see because of the geometric effect, when omega is larger than 2, the wave is actually amplified while moving down in this atmosphere. And similarly, we could also plot the solutions of weak shock and the strong shock in this diagram. They are shown as the red and blue line. You can see both of these lines are lower than the green line because of the dissipation. But all three curves monotonically increased with the omega. So that's why the shocks could be long-lived, while if the gas density profile of the atmosphere is steep enough. Of course, this is just an analytical argument. We further perform numerical simulations to check this point. And in the simulation, we model the propagation of 1D shocks in the atmospheres with different omega. For example, in the right panel, the curves show you the evolution of shock strings, while the shocks move in the atmospheres with different omega. You can see generally when omega is larger than 3, the shocks could maintain their strength over a large distance. So I think here one may follow-up question is how steep the gas density profiles are in real galaxy clusters. In this slide, I show you some X-ray observations. The solid lines show you the logarithmic slope of gas density profiles in 12 galaxy clusters presented in Vihilini 2006. So you can see generally beyond R500, the gas density profiles of galaxy clusters could be as steep as R2-3, and this observational result suggests that there is a habitable zone populated by runaway merger shocks outside R500. But here I have to emphasize that in the current X-ray observations, to detect these runaway shocks in the habitable zone is difficult because the gas density is low in this region. So we need thinner or links. And on the other hand, the radio observations could be very helpful to detect these runaway shocks, because we know that in merging clusters, merger shocks sometimes associate with radio relics in the outskirts of galaxy clusters. So we further model the synchronous radiation from runaway shocks, shown as solid lines in this figure. They represent synchronous emissivity at different radio frequency. So you can see the key feature of this result is that all the strong synchronous radiation is always confined to a narrow radial shell just behind the shock front. And generally, this feature is consistent with the geometry of the radial relics found in the peripheries of galaxy clusters. Like in this right panel, I show you an example. The white contours show you the radial relics found near the cluster zero radius. So here, I think one may ask, on the left side, it shows the runaway merger shock in a theoretical model, and on the right side, it shows the radial relics in observations. So can we really connect these two things? So maybe we can. In this figure, I show you the X-ray image of the coma cluster overlaid with radial contours from WSRT, and there is an infalling group NGC 4839. And we carefully model this system, showing the right panels. This is model X-ray image, and this is temperature. You can see in morphology, our model provides a good match to the observations. And in our model, the group is close to its epicenter. And the merger shock marked by the red dashed line has detached from this subcluster and moved to the south of the main cluster. And in position, this runaway shock coincides with the radial relic found in the coma cluster. So for this reason, we believe that in this system, a runaway merger shock driven by NGC 4839 is moving somewhere here, associated with the radial relic. And more interestingly, we found that in our simulations, we found that a well-developed runaway merger shock actually has an N-shaped waveform. The aforementioned runaway merger shock is actually just the leading edge of this N wave. There is another trailing edge, which is much closer to the class center. And the typical distance between the trailing and the leading edges is up to microparsec scale. In this lab panel, I show you it illustrates how the N wave is formed in the stratified atmosphere. So you can see at the beginning, when the shock becomes weaker, a rarefaction emerges. And as a wave propagates, this rarefaction becomes sharper and sharper, and it eventually becomes the secondary shock of this one N wave. And in the right panel, I compare the formation of N wave in the atmospheres with different omega, say different steepness. So you can see when omega is larger, the N wave is formed faster. So it means actually the gravity significantly promotes the development of the N wave. And the main reason is twofold. First, as I discussed before, the steep gas density profile could help the shock to maintain its strength. So the N wave is formed faster because the nonlinear timescale is always inversely proportional to the wave's amplitude. Another reason is that in the gravity could significantly modify the waveform in the inner region of the cluster, where the pressure scale height of the atmosphere is the smallest. And this point is more or less like an effect of dispersion. Here I show you the dispersion relation of the sound waves in the stratified atmosphere. You can see these red curves. So when the wavelength of the wave is comparable or larger than the scale height of the atmosphere on the left end, the dispersion relation is flattened. So at this end, the group velocity of the wave is much smaller than the sound speed. So you can imagine for a perturbation, its long wavelength component is always confined to the central region of the cluster because the group velocity is small, but the short wavelength component could propagate outwards with the speed of sound and construct the substructure, a sharp structure like the trailing edge of the N wave. So that's why the gravity plays a significant role in the development of the N wave. And in the right panels, I show you the formation of N wave in our cluster merger simulations. So you can see the runaway merger shock, say the leading edge of the N wave is marked by the red arrow, and the trailing edges are indicated by the black arrow. You can see after the core passage, the N wave starts to form, and it becomes more and more prominent. But once we see this structure in our simulations, we say, okay, we have to check the coma cluster to see if we can really detect this N wave in real observations. And this panel shows our model for the coma cluster. The black arrow marks the position of the trailing edge of the N wave. And along this direction, actually, the shock has been identified 7 years ago from the Planck assay image, and also in the XMM Newton data. Though at that time, no one really realized there is a connection between this shock and the radio relic at large cluster radii. So I think one most interesting point of this finding is that the radio relic in the cluster outskirts and also the X-ray or S-state shock in the inner region of the cluster, and also the infalling group. These three objects might parsec away from each other, but they actually have the same origin. They are all natural outcome of a single merger event. So, but this is still not the end of my story. In the next few giga-years, this runaway shock will continuously move in the outskirts of coma cluster until it encounters the accretion shock at the boundary of the intercluster medium. So what's going to happen when the runaway shock and the accretion shock are colliding? Generally, three discontinuities could be formed in the shock collision. One is the forward shock. The other is the reverse shock or rarefaction, and also a contact discontinuity in the middle. And in our specific problem, the collision between runaway and accretion shocks, the forward shock is mostly interesting. So we call it merger accelerated accretion shock, MA shock. So MA shock is interesting because it's powered by a shock, by a merger rather than the accretion. But at the same time, the Mach number of the MA shock could be very large, which is approximately the product of Mach numbers of two colliding shocks. So which means the typical Mach number of MA shock is up to a few tens to a few hundreds. And we further use 1D cosmological simulations to study how the MA shock are formed during the shock collision. This panel shows an example. The color represents the gas density. X-axis show you the cosmic time. Y-axis is the radius. So you can see at the beginning, the ordinary accretion shock is formed, and we initiate a secondary shock at t equals 2.5 giga-year to mimic the runaway shock. The secondary shock quickly catches up with the accretion shock at this point. So you can see after the shock collision, the MA shock is formed. You can also see the contact discontinuity formed from this shock collision. So after this point, you can see the atmosphere of the halo is significantly expanded by a factor of up to a few. And in our simulations, we found that there are two main parameters to determine the evolution of MA shocks. One is the Mach number of the runaway shocks. The other is the cluster mass accretion rate, gamma. So in these two panels, the curves show you the evolution, the trajectories of MA shocks when these two parameters are different. So typically for galaxy clusters, the MA shock could survive for a few giga-years. So which means most of the strong shocks we observe as a boundary of galaxy clusters are actually the MA shocks rather than the ordinary accretion shock. Another interesting point about MA shock formation, MA shock front is that there is a high entropy shell formed between the MA shock front and the contact discontinuity. So you can see in this gas entropy profiles, you can see the high entropy shell here. This is our 1D simulation results. And in the full 3D cosmological simulations, you can also see this high entropy shell here. In this figure, the solid lines show you the identified MA shock front. And this high entropy shell could further excite hydrodynamic instabilities in the class outskirts and may contribute a significant fraction of non-thermal pressure for this area. And finally, I want to briefly discuss Stephen Walker's new paper posted earlier this year, where they identified two giant contact discontinuities in the outskirts of the Perseus cluster. So we argue that the outer edge could be explained by the contact discontinuity formed in the collision between the runaway and the accretion shocks. So as a comparison, I show you the one of our 1D simulations. The color represents the gas entropy profile. So you can see the contact discontinuity formed from the shock collision is here, marked by the black arrow. Actually, there are two main points make our MA shock scenario attractive. One is that both the runaway and the accretion shocks are broadly tangential to the cluster radial direction. Those should be the structures of their collision. And this is generally consistent with the geometry of the structures we see in the Perseus cluster. For a more clear view, I overlay two circles in this image. So you can see both of these two edges are tangential to the cluster radial direction. Another point is that the second edge is near the visual radius of the Perseus cluster. And in our MA shock scenario, we know that the ordinary accretion shock is usually not far from the visual radius, and the contact discontinuity appears at the initial position of the accretion shock, and has a relatively small velocity in the rest frame of the cluster. So this make our MA shock scenario automatically match the observations. And regarding the inner edge, there are generally two possibilities. One is that these two edges are formed in the same shock collision. The outer edge is a contact discontinuity, and the inner edge is a reflection. And the other possibility is that these two edges are both contact discontinuities formed in different merger events. So this is my conclusion. And I want to emphasize 2 points. One is that the evolution of merger shocks could be summarized as a driven phase and detached phase. In the detached phase, the shock propagation is only determined by the surrounding atmosphere. So there is a habitable zone beyond R500 where the runaway shocks could survive for a very long time, and they will eventually overtake the accretion shock and form the MA shock. The MA shock will significantly reshape the baronic boundary of galaxy clusters. So I will stop here. Thank you for your attention.
Thank you very much.
Thank you very much for a great talk. Do we have any questions? If there are any questions, you can raise your hand with the Zoom feature or put them in the chat.
I don't know how to raise my hand.
You can go ahead and ask.
So this is Bill Foreman. I'm having trouble to find how to raise my hand, but I still have a question anyway. So most of the radio relics, it seems at least at the moment, especially in the one in coma, come from just at least this in coma, it's the detached shock. And should one also expect to see radio emission for the MA shocks and for shocks that are really, running off into the really, really outskirts of clusters?
I think the answer is twofold. I think on the observational side, the MA shock is really far from the cluster center, roughly 2 or 3 times visual radius. So I don't know if observations could really touch this region. And on the theoretical side, I think the challenge is that the gas density is really low there, and also the difficulty about modeling is that we need electron density, but in this low density region, actually the SAM is a collisionless plasma. So it's really, actually in the simulations, we only model the gas, but not separate the ions and the electrons. So it's difficult to know the electron temperature. Like that's why it's not only it's not a problem only for the radio emission, but also for the like X-ray and ST emissions. So I think that's a challenge for modeling the observational signatures of the runaway shocks at large cluster radii. But I think it should be there because the typical Mach number of the MA shock is a few tens or a few hundreds. So it's strong enough to trigger the bright synchrotron radiation.
And then if there are no other questions, I have one more question. No other
I
questions?
don't see any other questions so
The
far.
other question I have is there anything that we should expect to vary as a function of redshift? Should the relics or should the accretion shocks, the merger and accretion shocks, should they become more easily observable, less easily observable? Should we see anything different as we go to higher redshift, given that the filamentary structure may change, or is everything just scale perfectly?
I think the high redshift, maybe we mean higher than redshift 2. I think if it's later than redshift 2, there shouldn't be much difference. But higher than redshift 2, I think there are more filamentary structures. Here, the MA shock I discussed, I think they are mostly prominent along the non-filamentary directions. Otherwise, the gas density profile would be shallower, so the MA shock wouldn't be prominent. Another important fact, I think, is that it's the cluster mass accretion rate. And so we can imagine if the mass accretion rate is strong enough, the MA shock will be pushed back to its original position very quickly. So actually, this parameter is a function of redshift. When redshift is higher than 2 or 3, the mass accretion rate of the halo is much higher than the value at low redshift. So that's actually a composition. At high redshift, the merger rate is higher, but at the same time, the mass accretion rate is higher. So I think the overall effect is that it's a little bit more difficult to see the MA shock in the high redshift. But here, high means redshift higher than 2 or 3. That this value may be too high for galaxy clusters.
Yep. Okay.
Okay, thank you.
Thank you very much.
Was that another question? I think we might have time for one quick one before we move on. No? Okay, thought I heard somebody. Well, if anybody does have any further questions, our speaker schedule still has a lot of spots open, so feel free to sign up. So moving on, our second speaker today is Dr. Kristen Dage. She is nearly a doctor, just very recently defended her thesis, so congratulations on that. She newly defended her thesis at Michigan State University, working on ultraluminous X-ray sources and extragalactic globular clusters, which she'll be talking to us about today. Currently, she just started her postdoc at McGill Space Institute, and her research spans quite a bit of the spectrum, from X-ray studies to UV photometry to optical spectroscopy. So please take it away.
Thanks, Ruchu. Yeah, so I wanted to talk about Evoluxes and globular clusters because I think they're special and exciting, and they can tell us a lot of things about accretion physics and globular cluster dynamics. But I think it's always good to define your acronyms. So Evoluxes are, ultraluminous X-ray sources. They're super bright, way brighter than they're supposed to be because they tend to exceed 10 to the 39 ergs per second. I heard somebody refer to this as sort of a speed limit, and I really like that. So the 10 to the 39 is the Eddington limit, of course, which says that, you can only accrete so much material off given your mass. So if you are a 10 solar mass object, then your speed limit is 10 to the 39 ergs per second. And, some of these objects are going way over the speed limit. So they've mostly been identified in young star-forming regions of galaxies. This picture is a really famous example of one of them. And because they're in these young star-forming regions, we think that there's a massive donor star that's feeding them. And something super cool, there's evidence that the compact object is not a black hole, but a neutron star. And so this was a discovery in 2014. and they discovered coherent pulsations coming off of these ULX. And since then, they've actually found about 7 total sources that might be neutron stars, which is crazy because that means these things are accreting at hundreds of times above their Eddington limit. So they're just really going past that speed limit. So some possible explanations to explain how something with so little mass can get so bright. It usually involves the high mass donor star, like we said. There's possibly geometric beaming involved, or like some beaming factors. And then there's also evidence that these sources have like really high magnetic fields, like even on the order of 10 to the 15 Gauss. In this case, the magnetic field would help pull down extra material and make it brighter. I'm not going to talk about those. I'm going to talk about the ones in globular clusters. I really like globular clusters. And I realized I got bees back in May, and watching the beehive made me realize how much like a globular cluster it is, you know, because it's these collections of just, you know, tens of thousands of stars all bunched together, but they, you know, it's dynamic, just like a beehive. It's, you know, it's like, I think this image can be a little bit misleading because it looks like it's just static, but there's a lot going on there, and it's a busy, busy place, just like a beehive. And we found 17 Evoluxes in globular clusters in the past 13 years, which is crazy. And these globular clusters that host them are all associated with elliptical galaxies. So these are very old populations. So they are super hard to find. They're really weird and they're hard to study, but I think it's really worth the trouble because we really think that these are black holes. And so this is one of our leads on the question of black holes and globular clusters. And going back to those neutron star ULXs, it's so very hard to say that a neutron star could be the primary in a globular cluster ULX because all of the conditions required to like form and evolve a neutron star ULX are not met in this dynamic system. And so I broke down all of the ways in which they're different, and I have a little image to represent each of them. So for the star forming ULXs, these are, I got chickens in March too. This one is named Steve Z and this one is Jay. And I think they're a great representation of a binary because these two chickens are inseparable. And just like star forming ULXs, both of them evolved together. So they grew up together and hung out together like for the entirety of their existence as a binary. They're associated with young systems. So because we have a young system here, we can have a high mass donor star. And then remember that we also have evidence for our high magnetic fields. Now, by contrast, globular clusters are an old population. So that means they're a couple of grumpy old Muppets that had to go through a lot of work to find each other. And globular clusters, being the dynamic place that they are, tend to have dynamical evolution and something called preferential mass exchange, where any object in a given binary can swap out its partner for a more massive nearby star as it gets passed. So that means that the object that you were born with in your binary is not the one that you grow old with. And then there's not a lot of evidence for very, very high magnetic fields within globular clusters. So these are kind of all of the reasons that point towards the ULXs and globular clusters being black holes rather than the flashy high magnetic field neutron stars. So, okay, so what can these sources tell us? So obviously their accretion physics is going to be very interesting and different, but also in today's multi-messenger universe, it has this really nice connection to the emerging black hole binaries detected by LIGO. And part of why that is because globular clusters really represent the best place to form black hole binaries. But there's a problem here because it's a really long going question in astronomy since the 1970s of whether or not black holes can even stay around in globular clusters. Obviously, as older populations, globular clusters are a great place to form black holes. But back then, they thought that as soon as the black hole was formed, because of gravitational effects, it would just get kicked out of the cluster right away. Now, newer simulations are showing this may not be the case. Okay, so far, what do we know about black holes and globular clusters? The answer is not much from an observational perspective. There was not any observational evidence for a black hole and globular cluster until 2007. There have been some groups that have searched for black holes and globular clusters in our own galaxy within the last 10 years. So we're talking about 10 total black hole candidates in globular clusters in our own galaxies. So Laura Chomiak and Jay Strader have identified 8 candidates. And then Geezers and also the people behind the Muse survey have actually confirmed 2 black holes in the globular cluster NGC 3201, which is really exciting, but these methods don't work outside of our galaxies. So if we want to learn about black holes and globular clusters in other galaxies, we have to use different methods. And these Ulxs are the perfect sources to go and identify them. And so in practice, how we actually do this is we take the X-ray coordinates and we match them to optically selected globular clusters. And this is convenient because that means that any Ulx that matches to a globular cluster severely reduces the chance of that just being a background AGN, which is convenient. But these sources are really rare. So we've surveyed 10 galaxies at this point, which is tens of thousands of globular clusters. And we've only found 17 of these. But we have successfully studied these both in optical and in X-ray. And the optical is really interesting because some of them actually produce these forbidden emission lines. So this is one of the ones that does that. So what you're looking at here is its optical spectrum. So we have a flux and a wavelength. All of this little stuff here, this is the globular cluster continuum because all of our tens of thousands of stars are contributing light. But you can see that above the globular cluster continuum, we have these weird, this one's an oxygen emission line, and then this one is nitrogen. So that's interesting. And there's this other one, my favorite source, has this really cool optical spectrum. So again, this is its globular cluster continuum. This is about 10 years worth of monitoring on this too. And it also has the O3 emission, so the doubly ionized oxygen, but it actually has this weird complex, this weird shape. And so this is our 4959 doublet emission, and this is the 5007 emission, and it has this core and then these wings. And what's interesting is that some other studies have shown that there's not a lot of hydrogen above the globular cluster continuum, so that we know that in our system, we have a lot of oxygen, but no hydrogen. So that's implying that our donor star is actually a carbon-oxygen white dwarf, which is neat. And we can look at how this spectrum has evolved over time as well. So you can see that this is the flux in each of the components I pointed out of the 5007 emission. And for a long time, it was just going down, down, down. And we honestly thought it was just going to turn off. And then 2 years ago, it actually turned around and started getting brighter. It's completely unexpected. We don't have a model for it, but it just goes to show that, every time you think you have a source figured out and you're going to predict what it's going to do next, it just says, no, I'm going to do whatever I want to. So I just think the source is really neat. But so as far as our 17 total globular cluster Evoluxes, I think it's really good to compare them and ask what makes a source interesting. And one of those things that makes a source interesting is if it has a very metal poor or a very metal rich globular cluster. And, is there anything special about the clusters that host Evoluxes? And this question kind of arises out of some studies that have said that low mass X-ray binaries are preferentially hosted by redder globular clusters. And this is the sample of the 7 Evoluxes that we found in M87's globular clusters. And one of the things that I think is so interesting about this is that you can see that in terms of brightness, brighter clusters, which are also larger clusters, preferentially host our, Evoluxes. But we seem to have a huge disparity, and we can have, more metal poor ones and more metal rich ones. And so it doesn't really seem to jump out at you that, the color, like the metal of the cluster has anything to do with whether it hosts Ulx, which is kind of surprising. And this is something where if we can keep looking and find more of these sources, then I think it would be good to do a comprehensive study, but it's a little bit difficult too, because you also have to consider the nature of all of the clusters within the host galaxy, which is why I'm only showing M87 in this. Other thing that makes it interesting is if it has extreme variability. So like within an observation like this light curve is showing here. And some of them are actually variable on the scale of hours. This one I find interesting. So you can see that it has a drop within the observation, and the count rate jumps down. This one was bright in X-rays for maybe at least 10 years that we know of, but in 2003, it just turned off seemingly forever. There were some deep observations in that area that were taken in, I think, 2015 that we checked, and there's nothing there. So that's interesting. This one also shows this really high, variability. This dropped by about a factor of 7 within 4 hours. This source is still going strong, and we're still monitoring it and trying to figure it out. This is one of the sources in M87 we just found, where for some of the observations, it shows a lot of variability within the observation, and then sometimes it does nothing. But for the most part, the others really aren't variable. And so 14 out of 17 of all of the ones that we found don't vary within an observation. So that's weird. And then they can vary long-term. So these are some of our friends from M87. And some of them, can bump up to 10 to the 39 and, hang out there. Some of them just vary a little bit. So we have just like this wide range of behavior and variability. And this one is a source I really think that's worth highlighting, because you can see that it really, over about 16 years, it varies all over the place. And I like to point out these 2 data points. So these 2 data points were taken a week apart from each other, and yet it dropped in order of magnitude. So, it's interesting because I would say, if I'm being generous, about half of these sources vary on a time scale of months to years, but they don't vary in the same way. So this can tell us a lot about the accretion state. And so it means that they don't all have the same physics driving their high luminosities. And then the last thing that we want to consider is what is its spectral shape, and how does its spectral shape change over time? So this is an example of one of the spectra of the M87 sources. And we found that they were either best fit by just a black body disk model or by a power law model. And what's interesting, so this is pretty much all of the ones that were fit by a disk. So it's a little bit of a messy plot. The ones with the darker points are all from M87. The ones that are faded out are the previously studied ones. And you can see on this axis, we have the X-ray luminosity. And then down here, when it goes away, there we go. The x-axis is the black body disk temperature. And what's interesting is that most of them seem to have higher temperatures, like above 0.5 or above 1 keV. And they have all sorts of behaviors, but there's a couple of ones down here that are faded out that have lower temperatures. And what's so interesting about these is that these are the ones that host the optical emission. So that means that the sources with optical emission have really, really different behavior in their X-ray than the ones that don't seem to have optical emission. And then lastly, these are the ones we're best fit by power laws. This is really, really a mess. But you can see that there's a source over here that's just sticking out and being weird. So, so to finish, I guess, I would say globular clusters is a really exciting place to be. We've established with our larger sample what's unusual or like what's usual behavior. Lots of different behaviors, and I think we can hopefully start to differentiate different types of systems and their different accretion physics. You know, I gotta go drink some water because I'm about to lose my voice, so that's all.
Great. Thank you very much. I believe that was the end of the talk, or do you?
Yeah, I'm sorry, that was the end.
Okay, thank you. Thank you for the talk. Hope you got some water. And yeah, anybody have any questions? Please raise your hand or put it in the chat. I do see one raised hand in my chat. My window of participants has disappeared, but yes, I think Bill has his hand raised.
It's actually Bill and Christine together, both had the same question. We wanted to know if there was any information on the locations of the X-ray sources in the globular clusters, perhaps not for the distance ones, but for the couple that were in our galaxy. Is it known exactly where they are? Do you know where they are? Or even the ones where they are? Outskirts, core?
Oh, you mean in the core? I'm really not sure about those. I know that the ones in NGC 3201, so they measure those, and those are kind of, I want to say, like both below 10 solar masses, but I'm not sure if they're in the core or not. That's probably easily in their paper. I just forgot.
Okay.
Be curious. It'd be nice to look at, just because maybe if they're really massive, you might expect them.
Yeah, I think for them, I don't know if we were in the core or not, but I kind of remember from a talk they gave that they were just sort of mixed in the cluster, and that they thought that they could find a lot more stellar mass black holes in the same cluster.
Okay, thanks.
Thank you. Other questions? Bill, your hand is still up. Is that for another question or just?
Nope, that was the same question. Sorry.
Well, I do not see any other questions, either raised hands or in the chat. Was that somebody speaking? Or not? Okay. Well, I guess we might be ending a little early today. Thank you again. And if anybody does have questions later, you can email Kristen. So thank you again to both our speakers. Thanks everybody for joining us. Hope you have a great rest of the week and see you next week. Bye, everyone.